Okay, so the first thing you need to know when getting started with the OpenAg device software is to clone the repo and install it into a local projects directory. So while this is cloning, we can look at some of the other repos we have in the organization. So there's the device software, which is this one. Then there's the cloud, which has everything that's running in Google Cloud Platform. And electrical is all of the electrical design files, the PCBs, and then the mechanical is all the SolidWorks and mechanical specific integrations. So by now, the software has cloned, and we can move into the directory. So if we do a quick ls, we can see all of the top level components. The two main ones that we're concerned with are device and app. App is the Django-based application that serves the purpose of providing the device on-device database and on-device UI. And then the device is the multi-threaded state machine that controls the reading from sensors, controlling actuators, running recipes, managing networking, and a few others. The other notable ones are running the software, testing the software, type checking the software, and installing the software. So let's go ahead and install the software. There's two options for install. There's development or production. Today we're going to be installing it for development. Really the main differences between development and production is the log level. So development has a lower log level, so you'll see more logs. And also with production, the software will start automatically on reboot by starting the software in an RC local file. We'll get into that in a minute. So while we see this, all this console output, let's jump into what the install script is actually doing. So the first part, this is all just getting the runtime mode for development or production, and then setting the subsequent log level based on whether it's production or development. Then it assumes that this script is being ran from the project root, so it should be ran from within the OpenAg device software folder. This set-e is a nice option so that each time, anytime there's an error, the install script will stop, so you won't be left with a strange configuration for your installation. You wouldn't want to get halfway through, have something fail, and then continue and have to clean up afterwards. So the main things the script is doing is it's calling all these subscripts, and you can just go through them one by one. To initialize the device config, all this is doing is creating a file called device.txt that's located in data/config. And what this has in there is just the name of the config file. So we're initializing this to be unspecified because we're not sure what device configuration we want to use. Really, the device configuration is used to set what the device type is. So as you can see in the top right corner of my screen, there is a PFC3, and this guy has certain actuators and certain sensors that are connected to specific I2C ports. We need to know what's connected where, and really the device config file is the routing for all of the peripherals, so sensors and actuators, and also controllers. So to initialize the directory structure, this is just creating a few folders that should exist. Then it updates the operating system. This is really just apt-get update, apt-get install. Make sure that there's Python 3 on the system. Same with Postgres. Postgres is our database. Then we're doing port 80 forwarding. This is nice for accessing the device UI remotely, and also, I guess, similar to port forwarding, we're setting up a remote, so we have a remote device UI and a remote SSH. We'll get into that in a minute. Then there's creating the virtual environment. It's nice to run everything in a virtual environment so all the dependencies are clear, and we don't end up with a mixed bag of different software versions causing problems for us. Then there's initializing the virtual environment activate. So each time the virtual environment is activated, this script is called. And what this is doing is there's a separate activate bash script located in the install scripts, and it's just calling that. So this is where I set all of the platform-specific information. So detecting whether the system is a Raspberry Pi, what version of a Raspberry Pi, if it's a BeagleBone, how we're going to communicate with devices, and what sort of communication methods we're going to use. So the next one is to install some cryptography dependencies. This is not too important. If you are curious, you can dig into it. And then the big one is, now that the virtual environment is activated, we can install the Python requirements. So if you open the requirements.txt from the project root, you can see all of the different Python dependencies that we're using. And if you ever extend this software and add in a new module, make sure to put it in the requirements file. Next, we're setting file ownership, so we can run without sudo all the time, and then installing the network utilities. So there's a lot of network scripting in here that's used to toggle different Wi-Fi access point modes, connect to Wi-Fi networks, list the available networks that the device can see, and so on. And then we create the Postgres user, and this is the owner of the database. So then we create the database and migrate the database. And the purpose of migrating the database is to sync all of the models that are located in the Django app to really map that into tables into the Postgres database. Then finally, we're creating the project users. These users are when we log into the device UI in a minute, we'll enter the password, username and password, OpenAg. This is where that's being created. So if you want to create something that's a bit more secure and custom to your application, this is where you'll do it. Finally, we're initializing RC local. Again, like I mentioned earlier, RC local is used for all of the initial project or the initial loading of this software. So it's starting the software in production, and then in both production and development, it's setting up the port forwarding so we can always access the device UI remotely or SSH into the device remotely. So by now, our installation is complete. We have a few usage instructions. There's a normal mode and a simulation mode that we can run in. When running in normal mode, this is going to communicate to all, it's going to expect to have real hardware, and if it doesn't, it will throw errors. And then for simulation mode, this is everything simulated. So the simulation happens at the I²C level. So each time we want to, say, get a temperature value, we're sending bytes over the I²C bus, and the I²C bus returns some bytes. This simulation will just pretend that those bytes got reported back without ever actually trying to communicate with a real device. And finally, there's accessing the UI. So you can access it locally with the software that's running on the machine, or you can access it via the remote UI. And this is just the OpenAg prefix with the device serial number at Servio. If you're curious, and just search Servio on the internet, you can figure out how it works. It's pretty straightforward. And then finally, a link to our documentation. So let's go ahead and run this. I have this connected to PFC3, and this connection is happening over using the USB to I²C IC. So really what that's doing, normally on like a Raspberry Pi or a BeagleBone, there's I²C hardware embedded within the machine. But on my laptop, I don't have an I²C bus, so I need to add one. And the way I'm adding one is to create that sort of communication bus over USB. So I'm using the FT232H to do this. It's a really nice chip. It gives you I²C. It can also give you SPI and just general GPIO. So it's really a great chip to have in the system. So I'm just going to go ahead and run this. You see it's getting platform info. Like I mentioned before with the activate script, each time run is executed, it's sourcing the virtual environment activate script, and in that activate script, it gets the platform info, so we can see I'm running on a Linux machine. We can get the remote device UI, and here we do see that I have the USB I²C enabled. Oh, I guess I don't have it plugged in. So then we're going to get some errors. So let me stop that. I guess that's a good check to look at. So now I plugged it in, and I can see that the USB I2C is enabled, so I can actually talk to my food computer now. Then a few other IoT config settings. This is a bit in the weeds for an intro video. And then all the different log levels, spawning up the different controllers, and loading the different files. So really everything gets spawned from this coordinator function, and the coordinator will spawn a resource manager, something to look at, how much memory we have on the device, and then the network manager is saying, all right, how are we connected to the internet? Then the IoT manager is, once we are connected to the internet, can we connect to the Google Cloud, and report data to the back end, and also communicate and receive commands from the back end. So if we go back up and open the device UI with that nice link we had, we get to this login page that I mentioned before, and the default password is OpenAg. And the first page is networking, so you can see your device IP address. Clicking this link is how you'll register with the cloud. Not too concerned with doing that today. I really want to show how to provision a system and just get communicating with the hardware to begin with. So if we go to the dashboard first, we can see that it's not very exciting. We don't have any sensors or actuators configured. All we have is the coordinator, the recipe manager, the network manager, the IoT manager, and the resource manager. And these are really just waiting. They're not doing anything. Really, so the system's just waiting to be configured. So here we see this is the same unspecified that I mentioned that's in the device.txt file. I'm running on a PFC version 0.3.0, so I can load that config file. And then I can go back to the dashboard and see, oh, I have all these new sensors and actuators. They're all in the process of being set up. I can refresh the page and see, all right, now some of them are transitioning to normal mode. Since everything is in a state machine, we're always explicit about what mode it's operating in. I find it just makes it easier to reason through the logic and just make a more stable system. So then there's the peripherals tab. These are dynamically generated. So if you add a new peripheral in the config, you'll see a new card here. And we can get into building these and how to create these specific functions in a later video. But the big thing that I want to do is to prove that, hey, the device actually works. It's actually listening to the software. So I want to turn on the light. And I'm going to get this error message that I'm in manual mode. Or I must be in manual mode, because right now I'm in normal mode. So the big transition from normal mode to manual mode is it's changing where the LED panel driver is listening for commands. So if I refresh the page, I can see I'm in manual mode, and what this is doing is now manual mode is only listening from commands that come from this specific card, that originate from these requests, as opposed to being driven by a controller or another method. So if we want to turn it on, we can see that our light comes on, and we have manual control over our light panel. I might as well turn it off. To transition out of manual mode and go back to normal, just reset the system, reset the peripheral. We can see the T6713 is still in setup. This is because it's an NDIR CO2 sensor, and it takes a little while for the heating element inside the sensor to warm up to take accurate readings. There's some other calibration modes or calibration functions for devices that tend to drift over time, like pH sensors and EC sensors, which are nice to have in the future. So if I refresh the page, I can see my LED panel is back in normal mode. And if I go back to the dashboard, I can see all of my sensors reporting. They're all healthy, running in normal mode, so I'm pretty happy. A bit on the sensors tab. Here is all of what the sensors are reporting. So my humidity is 40% relative, my air temperature is 24 degrees, and a bit on the syntax here. So this is reported, arrow, desired. So I'm trying to I don't have any recipe running, so I'm not trying to hit any set points, but the device will just report the temperature regardless. So let's get started and load a recipe. Might as well pick a green one that's a bit more visual. So a bit on the nomenclature here. So green is the spectrum, 15 centimeters is the illumination distance, so that is the distance away from the light panel. So as the plant grows taller and taller, if you're trying to maintain an intensity of 300 micromoles at the canopy surface, you'll have to reduce the illumination distance in the recipe. So if we start this recipe, we can see the device turns green, or the light turns green, and we start to have desired set points. So a quick note on the light is this is running a bit of linear algebra to solve for what channels, what intensities each channel should be at. So the light panel in the PFC3 has 6 separate channels that each have their own spectrums and individual intensity controls. Sorry, I should clarify, they have fixed spectrums with variable intensity control. So what this is trying to do is figure out, all right, we see each of these spectral bands to have a certain intensity associated with them, and look at all of the different channels of the light and see which one closely matches it. And then it solves it for each individual channel intensity with a non-negative bounded least squares solver. And there's some docs on how this works if you're curious. It does get a bit mathy, so be forewarned. And I think now is a good time to end this introductory video, and we will pick up in the next one.